Momentum, although not a fundamental property of matter, is conserved in collisions. The combination of mass and velocity of objects going into a collision must equal the combination of mass and velocity coming out of a collision. The mathematics of describing a multidimensional collision is beyond the scope of these videos. We will therefore limit ourselves to describing a collision in one dimension. In other words, we will describe the conservation of two objects hitting each other in line, much like a railway truck hitting another railway truck, limited to the train track they are on. There are other kinds of momentum, such as rotational momentum involving spinning objects, but we do not deal with these here. Our model of collision involves two objects hitting one another. When describing this situation, we have two distinct situations to describe: before and after a collision. We will limit ourselves to two objects per collision. Although 3, 4, or more object collisions do occur, they are much more rare than two-body collisions. There are also different types of object that can collide. Objects which are completely rigid and pass on all the kinetic energy in a collision are said to be inelastic. Here, kinetic energy and momentum are both conserved. Objects which undergo deformation and absorb some of the kinetic energy in a collision are said to undergo inelastic collisions. Momentum is conserved here, but kinetic energy is not. Describing collisions is very detailed and requires precise labelling of the objects. The mass and velocity of object 1 are usually referred to by using a subscript 1 next to the mass and velocity symbols. Here we shall simply call them object 1 mass and object 1 velocity. The other object in the collision should be called object 2 and have its own mass and velocity. If we just want to talk about the momentum of the objects, then we shall call them momentum 1 for object 1 and momentum 2 for object 2. We also have two situations which need describing: the time before a collision and the time after a collision. The time before the collision is referred to as the initial time, and therefore has a subscript I. The time after a collision is usually called the final time, given a subscript F. We need to combine the two descriptions to give a full account of the collision process. Object 1 before the collision would have momentum 1 initial. What do we know so far? Momentum is conserved during a collision. That is to say that the total momentum of both objects before a collision is equal to the total momentum of both objects after the collision. P for momentum 1I plus P2I equals P1F plus P2F, where F tells us it's the final momentum, the final situation after the collision. We need to add together the momentums of both objects before a collision to tell us what the momentum after a collision will be. If we have an object of 10 kg mass travelling at plus 10 meters per second, which collides with another object of 1 kg mass travelling at plus 1 meter per second, we will need to calculate the individual momentums of both objects and add them together. Object 1 has mass 10 kg and velocity plus 10 meters per second. The situation is one-dimensional, so the direction is given by the plus symbol, designating forward. The momentum of object 1 is 10 times 10 kg meters per second forward, or 100 kg meters per second forwards. The unit of momentum is the multiple of the stated mass and velocity units. If the velocity had been given in miles per hour and the mass in tons, then the momentum would be given in ton miles per hour. The important thing to do is make the units all the same. If you're using meters per second, as is the scientific norm, then always use meters per second. If you are using miles per hour, always use miles per hour. Don't mix units together and use miles per hour for one object and meters per second for the other object. Our second object is travelling in the same direction as the first object. It is, however, travelling much more slowly, as at 1 meter per second. The first object will eventually catch up with the second object, and a collision will occur. The second object has a momentum of 1 kg multiplied by 1 meter per second, or 1 kg meter per second. When these two objects collide, the total overall momentum will be 101 kg meters per second forward. This will be the same as the momentum of the objects added together after the collision. However, the collision can change the composition of masses and velocities between the objects, As these objects are inelastic, mass cannot be transferred between them, so the mass of object 1 is still 10 kilograms, and the mass of object 2 is still 1 kilogram. It's at this point that the calculations become complicated. For the detail of the mathematics involved, go to the Advanced Physics Tutor website, the Physics and Introduction textbook, Chapter 2, Section 2.24, and read the description of the two objects colliding in mathematical terms. The mathematics boils down to a final velocity of object 2 being 17.37 meters per second, and the final velocity of object 1 being 8.36 meters per second, and is derived by combining the mathematics of kinetic energy conservation and momentum conservation. In an inelastic collision, momentum is conserved, but kinetic energy isn't, so a calculation as above isn't possible. Instead, you have to measure the velocity of one of the two objects after the collision to calculate the velocity of the other. Situations where one of the two objects is stationary are much simpler to calculate, as the momentum of one of the objects and the kinetic energy is zero. For explosions, the same principles apply. Initially, the object has no momentum. The one object's mass is broken up into many other objects' mass, and they travel in different directions with different speeds. If you measured each of these objects' mass and velocity, they would total zero, as the momentum before the collision must equal the momentum after the collision.